So it's been a while. It's been more than 10 years. We were talking about it a few minutes ago.
Yes.
And actually, it's a weird way of meeting because we basically you were my best friend's fiance, girlfriend.
Oh, girlfriend.
Yeah, it was. You weren't together for that long. How long were you together for?
1 year and some months.
Okay, still.
Let's say 1 year and a half. And then I'm willing to have Alex to confirm.
I'll ask him. Actually, he says hello. I told him I had a chat with him way in advance and also a couple of hours ago, and he said, "Oh, please say hello to her."
Yeah, so hello to him back.
And then if he wants to know what you're up to, he's gonna discover it in the podcast episode anyway.
Yeah. Okay.
And so we met in Morocco, Agadir in the south of Morocco, where we both couples met. We were there surfing.
Mm-hmm.
You weren't too keen on surfing back then.
Well, that period. Well, I was still a volleyball player, so and I was kind of like terrified to.
I remember that.
To injure myself. So it was a weird situation where technically I was not supposed to do anything. I wanted to, and at the end I decided not to. I think Alex did it. It was definitely braver than me, and so he just did it, and it turned out to be a very great surfer. So I'm glad that he went on with his own passion.
It was a wise choice on your side, by the way. Remember, we ended up in hospital because of my girlfriend got injured.
Yeah, I remember that. That's actually true. So I was cautious, let's say.
Yes. I remember you were doing on the beach while we were surfing, you were doing physio for your shoulder.
Yes. I was, that's the, it's great playing sports at professional level, but I think we are built to do it up to a certain level, meaning that after some years I had injuries basically everywhere, so it was a constant, trying to recover parts of my body. And so I'm definitely physically older compared to a 30-something person right now.
What happened afterwards? So when you came back from Morocco, were you still in Bologna back then, studying?
Yeah. So what happened there was I finished my studies in Bologna, and it was my master thesis. Basically, so my master's studies were in physics of complex systems. That is a branch of theoretical physics, and where you do a lot of, let's say, maths, a lot of very complicated pen and pencil calculation, but also a lot of computational stuff. So basically, I trained myself into programming in different coding languages and into statistics, right?
Mm-hmm.
So with this stuff, you can just, go and try to tackle all those disciplines that provide you data. And now there are so many different things, so many different fields that are basically feeding us with tons and tons of data. We are in the so-called big data era, right?
Yeah.
Age. So from there, I started I first went to the United States for the first time to finalize my master's thesis.
Mm-hmm.
And then I started for a while, I thought to just do my PhD in the United States. At the end, I basically came up with a different solution that was a PhD between Bologna, Italy, and London. After London and after Bologna, so when I finalized my PhD, that again was on complex system and in specific network science applied to biological data. Mm-hmm. You start applying for jobs. You are in that period in which you have studied so much and you
can't
really
wait
don't
to
know
start
what
working.
You're gonna do.
Yeah.
Yes, you want to kind of find, you want to find your own shape, right? And
yeah.
It was so ridiculous there at that point, because right now I'm basically in a similar period too, that every time the target is moving, right? And so I applied. I wanted to go on and try to find new challenges, and I was very lucky to be chosen by a great lab, that is the Barbagi lab, that is a leading lab in network science in the world. And so I moved to Boston, back to Boston again.
They're based in Boston.
And now I'm based in Boston, and it's been 4 years, and 4 years and counting, and who knows what the future is going to be.
I was looking into the first conversations we had. I was trying to remember the first conversations we had when we were in Morocco. Since you happen to be my best friend's girlfriend with a PhD in one of my most intriguing scientific fields that I've ever found in my life, it felt like a dream coming true. So I think we talked a lot about complex systems. I had a very basic understanding, and I still have a very basic understanding. So I think it will be very useful to actually start from there. Mm-hmm. And so the way I got into complex systems was the movie Butterfly Effect. Uh-huh. And I got so fascinated by the concept that life as a complex system is completely full of situations in which, it's a bit of sliding doors kind of situation in which events that actually define what you're going to be in the moment after. Mm-hmm. And so that's what got me so intrigued. And so I started documenting myself, and I found out, what the butterfly effects came from, and Edward Lorenz, the meteorologist, and his attractor, and why the name butterfly effect, and then all the concept of being able to completely affect someone else's life on the other side of the world just by small actions, and the fact that small actions have big consequences. And all of that is the consequence of the fact that there's highly complex interconnected systems, such as the one we live in, and any biological networked system is complex in that sense, because the variables are infinite. And so we had this conversation about this subject, and I got so much into it that at some point I got lost.
Well, it happens to me many times, so that's basically my job.
I think our ability to understand complex systems is very much connected to our ability to use maths. Is that true, or?
Well, of course, yes. So complex systems. So so first of all, it's a very wide field. I'm not an expert in all the theories related to complex systems. So, for example, you mentioned the butterfly effect, you mentioned Edward Lorenz, and this is, for example, very much related to chaos theory, right? Yeah. And so, if we want to go basically back to what the butterfly effect is this dependence, right, on slightly different, for example, in initial condition or boundary conditions. And there is a lot of talking about this. There is also a lot of misconception about this, because I suggest you to go and look to when and how this butterfly effect was actually mentioned, and which was the discovery, right, that was actually connected to the so-called butterfly effect. And this is very much related to dynamics. So how things interact, how things evolve in time. And
so he was a meteorologist, and he was studying how weather would evolve, and figured out that it was nearly impossible to predict.
Exactly. And what I think is fascinating in that is that he started talking also about these systems with different type of scales interacting with each other, right? And this is pretty much related to this unpredictability and that Lorenz mentioned. And it's interesting how a problem that is dynamical falls then back to something that becomes, let's say, let's use the word topological problem, but let's say we fall back into, let's say, geometry, right? So stuff like fractals, right? So basically the surfaces where the dynamics is evolving. Okay. So I studied this stuff. I'm not an expert of this stuff. What I actually basically what I, in a certain way, I went after was how interconnectedness can be modeled. Okay.
Yeah.
So what do I mean by interconnectedness? Oh, I cannot speak today. Well, anyway.
Got it.
So
interconnectedness.
Exactly. So two Italian people are trying to speak language. That's the result.
I mean, but so, Anglo-Saxon people always have to spell things to each other to understand each other.
I know.
So
that's so funny.
I mean,
it's so funny here with different, let's say, with American people from different parts of the United States. Usually, you can assist to very funny scenes where they don't understand each other. But anyway, let's go back to the mathematics of connections, right?
Yeah.
So, if we want to put it, so we can talk about complex systems in very simple terms and why connection matters, right? Because what we define, when we define complex system, the easiest way to define them is to look into, to say, okay, I have a system composed by many different, let's say, agents, elements, right? I have information about each one of them. So let's say we're talking about Fabrizio. Fabrizio is 34, is almost 34 actually, right?
Yeah, very close.
If I remember correctly. Has a wife, has a kid, lives in Milan, and blah, blah, blah. These are properties of the single node, the single element.
I'm a node, right? Okay, cool.
Exactly, you're a node. And then there are, and then we can map many other people, your friend Alex, your wife, your kid, and many other people, right? And the idea is that how can we define a complex system? Well, a complex system is a system that where we observe the so-called emergent properties. So those properties that couldn't be predicted just by the characteristics of the single elements. So, and why connection matter here? Because it means that if it's not related to the properties of the nodes, it means that it's related to how things get connected with each other. So how we model connections, how we model interaction. Well, the easiest way to do it is with networks, right?
Yeah.
So networks are, let's say, the language of connections. Okay. You can get very, I think the results of network theory are very, very intuitive in many situations. Unfortunately, people don't really like to think in terms of interconnectedness. So many of the outcomes or a prediction that people at the beginning of the World Wide Web had by thinking that, this is a system that is going to be truly egalitarian, right? Where everyone will have the possibility to be seen and to speak their own words. If you really know what is the mathematics of networks and how things tends to get connected, what is the probability to be found, or how easily is to navigate a certain structure, these people would have understood how polarization, for example, would have been one of the outcomes, right?
Exactly.
So these results are intuitive. Other results that are intuitive and easy to explain, for example, is immunization, right? And the importance of vaccines.
Yeah.
But people don't like to think in these terms. So because the idea is that it's the single that has to work together with other people to create something that goes beyond the properties of the single.
Yeah.
So it's if you want to think in terms of ethics and moral, well, there is a very deeper meaning here.
Exactly. And it's, it goes towards the integration. It goes towards of course, the more complex you make an environment, the more likely rich the outcome is going to be.
Exactly. And
rich or unpredictable, depending on whether you live it with anxiety or positiveness.
Yes, exactly. Well, so for example, the same properties that would describe if your system is, let's say, interconnected and easily navigable, and so could be a positive, let's say, feeling about this whole description. It's also the same type of description that tells you how you can easily infect a system, right?
Yeah.
So depending on, the mathematics is exactly the same, right? So you are basically trying to understand what is the minimal number, for example, of connection that you need in order to reach everyone. Okay. Or what is the expected number of steps that are connecting to random individuals, right? Or what is the probability to randomly stumbling upon a certain content on the internet. Okay. So you can use these concepts, and you can go from social media to biological networks when we talk about, for example, drug efficacy, to or spreading of certain, or for example, if we want to talk about biological networks, we can also talk about a different dimensionality, that is, for example, the epidemiology, right?
Yeah.
The epidemiological part, up to, for example, terrorist networks, right?
Yes.
And spreading of a certain type of ideas. So that's why I chose this specific subject.
It's extremely fascinating. Talking about epidemiology, what I'm thinking of, we're going to have a lot of really hardly mentionable words in this conversation. Epidemiology.
Yes.
I'm thinking about, the comparison between a virus such extremely virulent virus such as Ebola, and the current COVID-19 situation. So I'm thinking about, a small, not connected tribe in Africa, where Ebola, who is very dangerous, ends up killing the whole tribe, but not spreading anywhere else because of the very low level of connectedness.
Yes.
And then on the other side, what we're living today, which is a very weak, way weaker virus than Ebola, and less dangerous, but extremely virulent in a very interconnected world.
Absolutely. So you totally got it. So there are two, let's say, so first of all, I have to mention one thing before starting this type of explanation.
Sure.
I am currently working on biological and chemical networks. I'm not in network epidemiology. I've studied this stuff and I love it. And so I'm going to butcher it a little bit.
To me, they sound the same. So I think you're entitled to say your...
But I'm just saying that if any expert is listening to me, I'm saying sorry, I'm going to oversimplify this, and please have patience.
Highly unlikely considering my network, but yeah, okay.
Well, so as you totally got the two aspects of the problem. So there is a spreading rate that is very much depending on the biological characteristics of the pathogen. And it's basically the ratio between a transmission probability and the recovery rate, okay? So you can have pathogens that are extremely aggressive, right? And then the problem here is that this is not, so this, basically this transmission, these epidemics, is on a network. So it really matters what is the structure of this network, okay? What is the architecture of this network? So according to the architecture of this network, we calculate what we call an epidemic threshold. And this epidemic threshold tells you basically defines the regimes, right? It tells you basically how connected is the structure, how navigable is the structure. So the example that you brought to us was a very non-navigable structure somehow. So there are regimes for which if the spreading rate, that is the first one, the one that is depending on the pathogen, exceeds the epidemic threshold, basically we reaches what we call an endemic state. So there is a finite percentage of the population that is infected, okay? While if we are in the other regime where the spreading rate is less than this epidemic threshold, what happens is something that we really like, right? That is the pathogen dies, right? Dies out. And so we won't see infected people in the long run, right?
Yeah.
So what it's really interesting is that whenever the structure of the network is what we call a heterogeneous network, or sometimes we call it scale-free network, and I can explain what a scale-free network is in a moment. Well, this epidemic threshold becomes very, very small. So what is the consequence? And this is a very bad consequence. It means that even viruses that are hard to pass from individual to individual can spread successfully.
Yeah.
And this is a huge problem. And what are these scale-free networks, right? So these scale-free networks are one of the most common types of networks. So for example, in terms of social network, you are I think you want to call yourself a social media surfer, right? If I'm correct?
Used to be that, yeah.
So you know exactly, like there are this huge superstar on social medias, right? So there are this great, I don't know, on Twitter, there are these people that have, I don't know how many followers, okay? And so in the moment, and these are the so-called hubs of the system, right?
Yeah.
They have a number of followers, a degree that is extremely higher than, let's say,
the average.
Everyone else. So it means that the system, why we call the system scale-free, because we say that there is not a representative scale. So the average of the average, if you pick all the Twitter accounts, right, and you do an average.
Yeah, the average should be like 300 followers per person.
Exactly. That is not representative of what you would encounter in the system. There are these extreme hubs that
have millions.
Completely in a different universe, right?
Yeah.
Or they're an order of magnitude bigger than what that average would tell you. So that average is what should define the scale. So it means that the scale is not representative. And so that's why we call them scale-free. But
gotcha. Do you exclude the scales, or they still affect the system, so you have to consider them, right? It's not like when you do averages that you take out the extremes.
No. Of course you count them. What I'm trying to say is that, for example, it's like saying a Bell distribution as an average that is very representative for basically all the individuals in that distribution. They are not that far from that average.
Yeah.
Okay. When you look into distribution that are on the other way, let's say a fat tail.
Yeah.
So they are not bell curves anymore.
Yeah.
They are asymmetric, right? And so you calculate an average, but there are a huge percentage, or let's say there are significant outliers that are very far from that average. So they are not well represented by that statistics.
Okay.
I hope that is not too technical, but
it is. I mean, it is technical, but I think I get it. So what you're saying is the distribution of IQ could be an example of a very well distributed average, where the average is actually way more concentrated in the center.
Yes.
So you have way less people that have 130 or below 80 IQ. And then on the other hand, the map of, let's say, followers on a social network, you would have an average, which is maybe, as I said before, like 300, and then you would have the influencers that are a lot and would have millions of followers.
Exactly. That's exactly what I was trying to explain.
Okay.
So it means that, again, this system, these people are, let's say, exceptional, and in a system like that, is actually the outcome of something very common in basically all of the biological social regime that we have observed so far. That is the principle of rich getting richer. So when a system is growing, where, like, when a Twitter, let's say when someone that is new to Twitter, logs in, and
he ends up following
Twitter
that influencer.
Yes, Twitter suggests you who to follow. So it means that you will go and with a higher probability towards someone that has a higher number of followers rather than a lower number of followers.
Yes.
So that's consistently you will go on, enforcing again this mechanism.
In the same way, someone who's got more connections has a very active social life. If he gets affected by COVID, he's more likely to then affect more other people.
Absolutely, and that's exactly. So again, you see how you. I like to think about science and physics and mathematics as finding similar patterns in different subjects, right?
Yes.
So, and network theory is very much about this, because it's incredibly interdisciplinary, and you can see this. So in the moment in which you start thinking about, okay, so what is my probability to connect? And so consistent, what is my probability to spread?
I want to understand better the correlation and the relationship, well, rather than correlation, the relationship between what you're studying and the field of AI.
Oh, yes.
Because it feels like there's huge potentials for the two to collide at one point in a positive way, but also in a very dangerous way.
Well, they already collided somehow. So there is basically there is right now neural net. So there is a whole, let's say, art about how to create these architectures. Okay, and I have colleagues of mine that are trying to investigate this from a mathematical standpoint, right? So again, then you go back and you leverage everything we know about how to make connection, how to study the interconnectors of these layers. Okay, what has happened in the past years is that with neural network, they tried to basically represent networks, or real networks, right? So and to basically create methodology to do what basically in the past the usual mathematics was able to do, and actually to improve it, right? So every time we're talking about let's say link prediction, this is something that a neural network that learns the architecture of a network is able to do too. Okay, so for example, what neural networks are able to do is to for example, visualize the network. Sometimes it's very complicated to visualize. For example, think about visualizing Twitter with all the connections. Okay, so what neural networks are able to do, think about neural networks as brains. Okay, so they're able to find an optimal space okay, that is usually we call a low dimensional space that could be up to, let's say, 2 or 3 coordinates, so something that we can even
the ones we can visualize, yeah.
Yes, where they find a way to put, let's say, the nodes that are connected to each other, okay, close in space, okay. So they translate let's say the property of the connection among these two, among nodes, into coherent coordinates into a space. Okay.
So they're proportional and precise one to the other.
Exactly. So this is really where you see merging the network theory that we have done so far with the capability of translating, let's say, with a neural network. So instead of just saying, okay, let me try to explain this in a better way, because I'm miserably failing. So what you can do is to say, okay, on a network, I would search for my neighborhoods to understand who my neighbors are, right? I have to look into the connections, right?
Yeah.
So in the space created by the neural network, my neighbors would be those closest to me. Okay. So it means that also, if I want to suggest new connections, instead of basically working with the network structure that I had since the beginning, I can use the neural network and do a local search and search for nodes that were not previously connected in the network that you fed to the neural network.
Okay.
Those nodes are potential new links. So this is where the neural network is helping you to predict new connections, okay? Because it has created a space where the geometry represents the connection, the topology of the network, okay? More or less.
Is it like us now building a new tool that allows us to map more easily networks? This is basically what neural networks are.
Yes, so there is a branch of, so basically there is a field, let's say there is a branch of neural networks that are called convolutional neural networks, and this type of graph convolutional neural networks basically find coordinates for the network
but
nodes.
It's not the only thing that neural networks, of course, allows us to do. Okay.
No. Neural networks. So there are so many different techniques, right? So we are not talking, for example, about image processing, image recognition in this moment, right? So I'm trying to give you an idea of the bridge between networks and neural networks, right? Okay. So right now, neural networks have been already used, and so there is this huge field to basically do network predictions. Okay. So to use this huge amount of data that, for example, I don't know, Twitter can provide, where you have both the connections between people and you have also a lot of contact on each one of the users.
The interactions,
Exactly. So you have a lot of information on the nodes, you have a lot of information on the interactions, and you want to, for example, suggest new content. You want to predict, for example,
how many shares a video is going to take.
Exactly.
Once posted by a specific person.
Exactly. Perfect. You got it right away. So when the complexity of the problem, of your prediction problem, goes beyond a certain level, it's easier to move the problem to neural networks right now.
Okay.
Unfortunately, when you do that, you tend to lose what? Interpretability the majority of the time, because we're still struggling very much with understanding exactly what the neural network is doing when it does the prediction. So the prediction is optimized to, I don't know, predict your new connections, right? So it does the task in a very good way, but the reality is that we still don't know exactly why it does that. So this is why people have been working more and more and more to improve the interpretability of neural networks.
Educate
because
them, yeah.
Because, for example, there is all this debate about bias, right?
Yeah.
So neural networks depend on what you're training on. If you're, for example, you are feeding images that comes from a sample that is not well balanced in terms of, let's say ethnicity. I guess you have already read about this type of things, right? The neural network will be biased because of the data.
So it will be racist and sexist because
Absolutely.
it's trained by a racist and
Absolutely.
sexist society.
Absolutely. Absolutely. So it's interesting how we are at a point in machine learning and AI that is a fancy way to talk about neural networks, because neural networks are not new. That is something that I want to remark every time. Now everyone is talking about AI, but neural networks are not new.
Yeah.
Okay. So buzzwords, let's say.
Yeah.
And it's amazing how right now we're going back to philosophy somehow, because in the moment in which these type of prediction tools become so relevant in our everyday life that our decision making depends on them, you need to very much think about what you're going to feed to that neural network, because it's going to be the picture of the world that you're going to see.
True.
So yeah,
it's a bit like a parent educating their child. It's very likely.
Absolutely. And so do we want to be as naive as people that were so, like, again, I was
is there like a how do you call it, a confederation or a group of people who are debating the epidemiological or philosophical consequences of all of this? Is there like someone who's posing the question and highlighting the threat there?
So I cannot, in this moment, I cannot really refer you to names, but no, it's an ongoing debate for sure.
Okay.
Like it's,
so you end
for
up
example,
maybe talking about it at the bar with a colleague, but there's not like an association who's saying, okay, we have to validate each thing because there's a risk here if we don't take in consideration every single aspect of it. There might be huge consequences.
So I am positive there are for sure, because of, for example, autonomous driving car, right? So that is point number one. And then I cannot point you right now because, again, we're touching so many different fields, and I, as a scientist, I'm happy to have this conversation because we are having a very nice brainstorming. But on the other hand, I also not always feel comfortable to tell you exactly what's happening in certain fields, because they're field of expertise, and I don't want to drive you on wrong conclusions. Anyway, I am sure that there are, because the debate has so broad that has touched also people like me that are not working. Like, for example, I'm working with neural networks to see exactly what we can use in a certain way, what we can learn and what we can acquire when we use neural networks rather than classic network prediction tools. But I'm not involved, for example, in all the complexity related to, for example, image recognition, or I'm not involved into the autonomous driving cars. So that is a different type of field. I am pretty sure that you will find plenty of material, because people are, I mean, especially here in the United States, we're having a lot of problems, especially with the image recognition softwares. So
yeah, I've actually Funnily enough, the person I interviewed before this episode, she's a person that I've met online searching for a solution for image recognition to automate the quality control process of our fabrics. And it was just very interesting, the connection we made there. And unfortunately, the project didn't fell through halfway through the project because it was too expensive. But that was another interesting application, in this case specifically of neural networks. And it's a weird one. Hopefully you appreciate it, though.
I hope so. I'm also scared right now.
What's your feeling about maths? Do you think it's more something we've invented, like any other scientific tool that allows us to investigate the universe, or is it discovered, like the source code of a video game?
Fabrizio, this is not a question for 1 minute.
Take your time. I mean, depends on what time you go to sleep. But...
It's a tough question. Okay, so
just go with the flow as you feel appropriate answering. You could even say, it's too complicated.
Okay, so on one hand, I strongly believe that it's considering that it's a language that is that I think is the let's say truly interspecies somehow. Like, again, if we have to, I'm thinking about how when we had, let's say, space missions, the Apollo missions and things like that, and with the idea to communicate with potential aliens. The only language that was chosen, of course, was somehow math, right? And the fact that it was clearly recognized as something that goes beyond the human species.
Yes.
Okay. Also because we observe it in the among animals, and so that's also the language that whenever we try to communicate, or there are experiments about communications with animals, it's our basic approach. I tend to say, if I really have to give you a very quick answer that goes with my gut feelings, that goes beyond the observer. On the other hand, then I would start going to quantum mechanics, and then it's another problem. So
look, that would have been my second question if we had more time. So if you want to touch on it, just do it.
Yeah, but you're a nasty interviewer, right? Because these are like these are tough questions that on which you could perform very poorly if you're not well prepared. So I would say, for now, this is something that should be. I can write you something about this if we are interested in continuing the discussion.
Yeah, I'm definitely interested.
Because it's I would love to. I actually lost the capability to work on this type of question because I'm kind of solving mathematics. I'm solving models.
Yeah.
But I got, I stopped doing philosophy somehow. And that's a pity because our work is so deeply embedded into philosophical questions. And I think that science should be taught by, going on also with very key philosophical questions that are dependent on the outcomes, and they could be both at the moral and ethical level, but also on the existence, right? On the whole existence and the consistency and the consistency of, let's say, of the language, right?
Yeah.
And how we arrive to, you know, who use this type of language, and is this language universal or not? So right now I'm fully aware of my limitation in this moment, and I don't feel in my best shape to actually answer to this type of questions. But I'm glad to hear that you are curious about this. So yeah, we should think about this stuff more.
Yeah, I'll tell you my point of view on this. So of course I thought about it beforehand, so it's not like something that I'm just throwing out there, even though it is a work in progress kind of conversation for me at the moment with my head. Probably I would go with it being something we've discovered, because the likelihood of this language to be by chance something we invented and also allows us to understand everything in the universe, included for so far even, you know, the way stars behave are millions of light years away. It can't be just, you know, oh God, I just invented something that's allowing me to uncover from biology to people's behavior to programming to astrophysics to astrobiology and so on, everything in the universe slowly. And of course, the more I uncover, the more I discover that I don't know. So maybe that's a rabbit hole in it. But it just feels like it's more of a discovery of something that's underlying, always behind. Even though, you know, with as you said, we get into quantum physics, and so we get into the world of, oh shit, there's behavior that I can't understand, and mathematically I'm struggling to predict or interpret and so on. So maybe it's a discovery of a basic language of the universe, and maybe there's more languages that we still have to yet discover. And with our brain and the potential of our brain, we're unlikely going to unlock by ourselves, and that's where neural networks will come in as a additional tool for us to actually.
So if I can add a very quick thing on this, is that they have already started trying to understand how to discover physical laws with neural networks. It's very interesting. It's a line of work that I've stumbled upon recently with my students while we were basically taught, like, again, we come from very different backgrounds, and of course right now we are learning neural networks too. Not because I'm in love with neural networks. I mean, I will never be the person that does neural networks all the time, but I think they are a very interesting tool that can be extremely valuable for prediction. And I find them fascinating for understanding them is fascinating and will tell us a lot about probably also how we work.
Yeah.
Said that, there is definitely a branch of neural network theory that right now is looking to how we make discovery. What is our discovery process? Okay. And how we can identify a physical law, for example, like, I don't know, gravitation. Okay. From data. So how can we learn this from the data if we are observing a certain type of experiments and we have no idea of
what we're going to find out?
The neural network doesn't know about Newton, let's say. Okay. So I think this is probably the most fascinating application that neural networks can have. And I am tuned to see what is going to happen.